Yeah, good morning and welcome everybody to the next lecture in Bioprocess Engineering. Yeah, here we go. Next lecture, Bioprocess Engineering. Indeed, it's our last lecture. Next week we only do calculations, and we will have a look in exercises and your questions. So the last regular lecture is today, but we start with calculations. So we start with the homework. So your homework, as you remember, was this algae batch growth kinetics.
All examples are taken from Pauline Duran, Bioprocess Engineering, 2nd edition. It's a wise idea to have a look in this book also.
So you remember what you were asked to do is you had whatever growth at different temperatures, 19, 20 and so on degrees, and it was slow growth, so the growth was in days, and you had the values. And what you had to do is, based on these values, first of all, calculate the specific growth rates. So I did that in Excel to make it very simple, very straightforward. So what I did briefly is I just transferred the values, Alan transformed it. That's of course the first thing you need to do. And then check on a plot whether it's exponential or not. So you have to identify your exponential phase, that's as always. And then you simply can, based on this plot, t versus ln x, you can then the slope, as you remember, is the specific growth rate. So this is what I did here. So here I have my temperature in degrees Celsius. Here I have my temperature in Kelvin. And this is then the mu max, and the mu max is simply calculated with a formula. And you see, as an example, this is the value of 19 degrees. This is then simply the times and the as the x values, and the ln x as the y values. It's the other way around, always in the slope. I don't know why they do it like this. And then you get this value. You do the same for the others. It's a wise idea. I already told you last time, plot these values in order that you really see whether you are in the exponential phase or not. If I remember correctly, that was all in the exponential phase, so that was not such a problem. This is then simply I calculated 1 divided by t, and this is then ln mu max. This is for the calculation later. And now an important step is I plotted the temperature versus the maximum specific growth rate. This is here. So temperature versus maximum specific growth rate. And usually, of course, you know that we have with our curves, you have an optimum and then it goes down. And exactly this is what you see reflected here. So you have here an increase in the specific growth rate. With higher temperatures, the specific growth rate goes up. And then this value at 28 degrees is way lower. So the question is, what happened here? It's very simple. It's too hot for these algae. These are algae. These are used to grow in aqueous environments, and aqueous environments with 28 degrees is rare. Usually they're adapted to lower temperatures. So this is above the optimal growth rate of them. So this is of course no more in an area where you have a correlation, a simple correlation between the temperature and the specific growth rate. In other words, this value you cannot take for using this Arrhenius approach. This drops out. And the reason is, and this is again, it's not maths what you're doing here, it's bioprocess engineering. The reason is because you say, these are algae, based on my data, either it's an incorrect measurement, or more likely it is that in this temperature area, we're above the optimal specific growth rate, and the growth rate declines. So we take out this value for the calculation. And then we plot this line, and you might remember what we did is So this was based on this equation here. I told you just use this Arrhenius equation and substitute the K with a specific growth rate, because this is the rate constant or rate coefficient, which gives you the where the speed of the reaction is calculated. And this is the specific growth rate. And then the log transformation is the linearization. And then you say, if you plot 1 divided by t, you get the slope ER. In our calculation here, we don't care about what is E, what is R. So we can take this complete fraction here as C, for example, and then we have ln A, and everything is fine, because we just want to get a mathematical correlation. We're not asked to get the activation energy, which is also in specific growth more or less meaningless. So that's not an issue. So now going back. So again, what I did here, I did this ln transformation, as you see. I transform ln transformation of mu max, and I 1 divided by T. Of course, you need to take the absolute temperature in Kelvin in these formulas. You cannot take the temperature in degrees Celsius, otherwise your results will not be correct. And then you plot it. And of course, you don't take the value of 28 degrees. And then you get this equation here. And of course, plus 13.547 corresponds to ln A, and this minus 3826.7 corresponds to C, and therefore I just transferred these values here. And of course, as 13.54 is ln A, A is then 7.59, and so on. And then this is then the equation here is mu max is equal to 7.59 times 10 to the 10 times e to the power of minus 3830 and so on divided by t. What is a wise idea? What I do then always, because this is not more work, then I just transfer this formula. So this is the formula. This is, you see, it's this value fold e to the power of this value divided by 18, and then sorry, not P18, by the temperature. So I transfer that in this, and I check whether my mu max calculated really corresponds to what I expect to, or whether I had an error in the formula. Obviously not. You see that my calculation fit well, and this really looks like this is this curve here, and everything is fine. Now, and the question was, now what is the value at 22 degrees? Well, you simply put it inside. So I put here 22 degrees, and here is my value. So you see, if you do such a thing in Excel, you can do it in, I think it was 10 minutes for transferring the data, and the remaining calculation was maybe also 10 minutes. So that's quickly done. And then I just solve. My x0 is this value, fold, this is the normal formula, x0 is equal, x is equal to x0, fold e to the power of mu t. So I just put in my x0, which is 2 times 10 to the 5. The t is after 2.25 days, and then I have my concentration, and then I simply multiply it with the volume, and finally I end up with 1.68 times 10 to the 10 cells, and that's it. So that was this exercise. So we go to reactor engineering, and we look at reactor configurations. Now that's really bioprocess engineering, the bioreactor. The last lecture we look at the bioreactor. That's the sad news, but the problem is always how to put that all together. And as we need some calculations as basics for reactor engineering, this is the order. So what you of course have heard already a couple of times, and what you already know, is how a stirred tank reactor looks like. And this is a typical feature of an aerated stirred tank reactor. So we have a liquid volume of 70-80% of the reactor, which is then, so it's not completely filled because we don't want to have the foam outside of there. And you see here we have a mechanical form breaker. We have things here where we can cool the reactor, baffles, sparger, and of course our stirrer. So the cool thing about stirred tank reactors is it has a stirrer, so therefore we can bring in high powers, and therefore it's an optimal bubble dispersal. Of course, there are limits. If you have shear sensitive cells, for example, animal cells and so on, there is a problem. And of course, you need to have an aseptical seal. And this is at the beginning, this was the difficulty for stirred tank reactors. You need a form control for a stirred tank reactor. That's normal, because if you sponge in, you will create form. And a design parameter, what you have in this is the height versus the ratio between the height and the diameter. And of course, the least expensive is the one with the lowest surface, because the steel is your cost at the end. Usually what you use is ratios of 3:1, so they're higher than broader. That's easier to put in your plant, first of all. And second, it increases oxygen transfer, because the liquid pressure on the down is higher, and of course the higher pressure increases then simply the oxygen transfer. So this also helps. So for bacterial cultures, usually the height diameter ratio is higher, so they're thinner and taller, and for cells it's usually lower, so they're thicker and not so high. So that's a general rule. The job of your stirred tank reactor is, of course, mainly, as you know, bring the oxygen in your liquid. And so this is the function number one. But the other thing is also you want to mix. This is the reason why I have a stir, that in order that you have conditions at all positions at your bioreactor which are homogeneous. And there you can look at how efficient the mixing is. You remember, as we talk about oxygen transfer, I always say that the mixing efficiency we neglected, because if we have a optimal oxygen transfer, at least in smaller bioreactors, we have a high mixing efficiency also. However, it's still important, because you remember what you do in a bioreactor. There is also a measurement control unit. You had an own lecture in measurement and control engineering, or you're still doing it, I don't know, with my friend Platte. And of course, your question is, why do I do that? Well, because you do that in the bioreactor. And now the important thing is, in the bioreactor, of course, if, for example, if I measure and control my pH value, so I have a pH sensor, and it's now at pH 6, and I want to bring it up again. So what I will do is I will pump in base in order to bring it up again to 7, for example. Now the point is, I pump the base, of course, not in homogeneously, it's pumped in on the top, for example. Now, if I have a 20,000 liters bioreactor, and my sensor is, my pH sensor is, for example, there at the bottom, this takes a while until this is distributed. And this is measured. And I can measure this as a mixing time. And it's not a standard definition, but the usual definition is that this is the time required to achieve a less than 10% concentration difference. So if you look at this, this means that if I have my concentration of my tracer, of pH or whatsoever, then this concentration initially is low. And then I put in a tracer, an amount of a tracer which would bring the concentration from the initial concentration to the final concentration. Now at the beginning, if I put it in, for example, on the top, and if I have my sensor at this side on the top, and I have a stirring, so this means I have a drop in, this high concentration now comes to my sensor, and I get now this peak. Now it's going down again, and then it's kind of oscillating towards this concentration. And as soon as I'm here, then I say, now this is my mixing time, how long it takes. And of course, this is all a function of where I inject my tracer and where my sensor is located. So that's important to know. The mixing time, you can say, must be a function. The faster my stir speed is, the better it is. Then it of course depends on geometric parameters of my bioreactor, like the impeller diameter. It of course depends on the viscosity of the fluid and so on. And this is all in the Reynolds number. And you can plot then, you see the mixing time as a function of the Reynolds number. And obviously there is a correlation. This is obvious. So this is, but at the end, you would have to measure that for your system because it depends on many other things at the end where you are located and so on. You see that in the case of turbulent conditions, this mixing time is not changing in this parameter where you have the stirrer speed and the mixing time, so it's a normalized mixing time remains constant, and then you have this empirical equation. But the interesting point is what you have in this equation, and this is why it's not the little man here. We have, of course, in this function also the power. The point is, of course, stirrer speed is related to the power input. The higher the power input, the higher is then your stirrer speed, for example. And the point is, when I want to increase now my volume, we have the volume here, what happens? So if you look, what happens if I change from volume 1 to volume 2? For example, if I make a ratio if I solve it to the power, and then I put in a volume 1 of 1 and the relative volume 1 of 100. And you see, if I put that in this equation, my power goes up, the volume goes up factor 100, the power goes up factor 2000. So this is the reason, if you want to scale up, that you cannot scale up linearly with your power. And large bioreactors, very large bioreactors, are not feasible as stirred tank reactors because you would require an enormous power input to achieve adequate mixing. So it's no problem to achieve adequate mixing with a stirred tank reactor in low scales. It's reasonable if they're in the reasonable scale. So you need a high power input. That's okay, but you can still bring it in. But would need insane power inputs if you go to really huge, large-scale bioreactors. These cannot be designed as stirred tank reactors. That's when I talk about 1,000 meter cube and so on. So really huge bioreactors. So, and also if you upscale, usually the mixing time and so on will increase because usually you don't get it that you can keep the mixing time constants over all the upscaling because this power, this linear, this exponential increase of the power you don't manage. Okay, now if you look how a reactor looks like, if you have a very small lab bioreactor, what you might have is you just have one impeller, so one Russian turbine. But usually you have more than one at different positions, even if at small bioreactors. Even our lab scale 10 liters bioreactors has more than one. So of course, this is then difficult also to predict the pattern inside of your reactor. So you will have then a dependency of the mixing time in the function of where you are. So if you're there in the middle, that your mixing time is really cool, but if you're sitting here, your mixing time is lower. So if you would inject something here and you measure here, it takes a while, and the other way around. If you inject something here and you measure it here, then it takes a while. So at the end, a more fair expression would be what is the maximal mixing time. So the most unfavorable condition. So obviously if you inject here and measure here, or inject here and measure here, that's cool. But if you inject here and measure here, this will take longer. And this is then, I would say, the most unfavorable one. And it's then, you see, then you can plot that as a variation of the mixing time in the function of where you inject your tracer. So that's obvious. Okay. So that's about stirred tank reactors, mixing time. And now we come to a reactor type where power input is less a problem. We come to a bubble column reactor. A bubble column reactor, by definition, does not contain a mechanical agitation. Then it would be a stirred tank reactor. So you see, it looks like a stirred tank reactor, just without a stir. So you have a sparger, and that's it. So in this case, all the mixing and aeration are achieved by gas sparging. You cannot disrupt bubbles and so on. So this is, of course, then a limitation. However, the advantage is that such a bioreactor requires less energy than mechanical steering. That's clear. You don't have a stirrer sealing here, so it's easier and at lower cost to realize. So it's cheaper, such a reactor. There are no internal structures, so it's easier to keep that clean. And this type of bioreactors are used if, for example, you produce in large scale like for example, baker's yeast. And here what you have is that the aspect ratios are go to a higher ratio with respect to the aspect ratio. So because the only way to get your oxygen transferred is, of course, or keeping the bubbles small, is the Sparger dimensioning. And of course, the higher it is, the higher the pressure down there, and the better the oxygen transfer. So these reactors are therefore, in general, designed small, high and thin. Okay, yeah, that's clear. So you cannot, as soon as the bubble is released, you have no chance anymore to interfere with your bubble design. So this means, in other words, that everything is about the Sparger and everything is about hydrodynamics there, so the pressure. If we look in how this bubble flow actually looks like, but you see, you get a kind of a chaotic pattern here. And at the end, this is what you want to have. But you also have seen it's certainly not an even distribution of the size of the bubble. So that looks chaotic. So however you want to be there, you want this heterogeneous bubble flow pattern. This is what you have seen here. You have seen that some of them are rising, some are going down, and this is very heterogeneous. And this provides the best mixing in this, because you have an upflow and a downflow fraction. You don't want to have a slug flow pattern where you have large bubbles just rising and exploding on the surface, and you don't want to have just such homogeneous bubble flow pattern. So this means that there is a relation between the gas velocity and the reactor diameter, and you see that there are then these transition zones, and at a certain position you can generate then this heterogeneous bubble flow pattern. The mixing, of course, depends only on what flow pattern you actually have inside. And of course, as you have seen, that it's no way to deduce there anything theoretically. So what you do is you measure, and try to find an empirical correlation. At the end, what you do, empirical correlation, at the end means you fit an equation through your data, full stop. And this is what came out. You can derive an empirical equation for the mixing time, and this is this equation here. However, it's a wise idea if you then work with a bubble column reactor in a larger scale. I would also measure it to be on the safe side. Why is it, for example, we talked about this this pH control. This mixing time, of course, is important, because if you just for you as what that means at the end. So I pump in my base. Again, I want to come from pH 6 to pH 7. Now, of course, if I have a stirred tank reactor or whatsoever, now I come with a high concentration there after bringing it in to the sensor. And of course, this high concentration at the beginning is just because the stirrer just brought it there, or because my bubble column reactor pushed this high concentration to the sensor. It will drop down immediately. So I need to adjust my sensor in a way that it waits until we have the mixing time is achieved, or it doesn't pump in too much. The mixing time then dictates my settings for the sensors in this case, in order how they control the stream. So that's at the point this importance. If you have already your things going on in your reactor, this is not an issue. However, your pH and antiform and so on, this is what you're at the end interested at the end. Okay, the oxygen transfer depends on diameters of the bubbles and gas holdup, and of course also there you have no chance to deduce a theoretical equation with respect to the oxygen transfer. Also, this has been done empirically, and this correlation has been proposed. It's we won't do calculations, also not in the exam here. It's just that you know it, and it's little man is not there, because of course you need to know that the oxygen transfer, on what it does it depend in bubble column reactors, and that the equations you can deduce, if at all, are empirical at this point. So that's the bubble column reactor. Just checking whether there are questions with respect to the bubble column reactor. Why wouldn't you want small bubbles? Okay, so that's a good question. The problem is, if you have small bubbles, what you get is, it's not small bubbles, it's this homogeneous bubble flow. So this means that you have very low. In this case, you see that your superficial gas velocity is low. This means that you sparge in a very low amount of gas. In this case, these bubbles cannot coalesce, so small is in this would be nice. However, what you don't have is this heterogeneous bubble flow pattern. So you have just upwards rising bubbles, but you don't have downwards rising bubbles, and therefore your mixing efficiency in this case is low. So it's not all about oxygen transfer, it's also about retention time, and the bubbles will disappear quite quickly. So in this case, in a bubble column reactor, this is not optimal. But it's a good question, because we come in the next part to airlift bioreactors, and there things are different. So you will see that. Yeah. So we come now to airlift reactors, and you will see that in airlift reactors, things are a bit different. What is an airlift reactor? You separate the movement gas without gas. Then you can set up a regular movement. In this case, what you do is you sparge in, you create an upward movement, and the down movement is separated, and this is without gas. And then, of course, you can sparge in way more air. In this case, you don't want to have this coalescence. In this case, you don't have this backwards reaction. So the dynamics and the mixing pattern in these reactors is way more regular. And here, optimally, you want to have this small bubbles, because you don't care about this downwards reaction. So it's not that you want to have this big bubbles, by the way, in the bubble column reactor. It's just if this pattern is set up, you will have a certain amount of bubbles which will coalesce, and that's what you have then in this case. It's not that you want to have that. It's just that this appears in this heterogeneous bubble flow pattern. This doesn't appear if you separate up and down flows. And this is what you do in airlift bioreactors. And you have different designs in airlift bioreactors. You have here a design where you have internal loops. So this means that you have a tube inside of your bioreactor, more or less. And if you sparge in this tube, you will have an upflow in the tube, and then the downflow is beside the tube, or you can also sparge at the side and you have the downflow here. But there are also external loop airlift bioreactors. So in this case, you sparge in here, and there is a separate downcomer tube, which is smaller, which just goes down. So also here, of course, the mixing is achieved by gas sparging. And the patterns here are more defined as in bubble column reactors. So in bubble column reactors, as we have said and we have discussed, it's very heterogeneous. That's what I want to achieve. So here it's clearer. And we have achieved that by separating up and down flows. Okay. Now, for external loop designs, the gas disengagement on the surface, so that the gas leaves actually your liquid, is more complete. It's easier to achieve because it's more regular. Therefore, you have a higher density of your downcomer fluid. That's clear, and that mixes then this pattern. And you can have higher circulating velocity. So you can really have a quite speedy process inside of that you will not achieve in a bubble column reactor. So the mixing you can achieve with these airlift reactors is better than in bubble column reactors, and it's more stable. So of course also there people have tried to derive empirical deviation, but so they didn't try to deduce theoretical equations. Makes no sense at all. But even empirical equations were unsatisfactory for mixing time and velocity and so on. As a rule of thumb for internal loop devices, this gas hold up, so the time the gas stays in your bioreactor and the mass transfer rates are kind of similar to bubble column reactors. The external loop devices, the downcomer, of course, is free of gas. Therefore, in this where you have no gas, there is no mass transfer from gas to a liquid, so that overall mass transfers are lower compared to bubble column reactors. However, you can construct these reactors with very, very high volume. So there are reactors with capacities way above 1,000 meter cube. It's no way to construct a still tank reactor in these dimensions. So these huge reactors are, let's say, the trademark of an airlift bioreactor. These height-width ratios are often really extreme. So you have very tall and very thin reactors often constructed. And of course, you have then very high hydrostatic pressures at the bottom. And that increases, of course, your mass transfer significantly. Yeah? So this also means that in a stirred tank reactor, we, let's say, did in our calculation, we thought that the mass transfer is all the same already for stirred tank reactor. This is not correct, because also there we have a hydrostatic pressure which is higher at the end. But if I have an aspect ratio of 100 to 1, of course that's tremendously different, because the pressure is 100-fold higher more or less at the bottom compared to the top. And that makes a huge difference with respect to mass transfer. Okay, that's an example for an air-lift bioreactor. This is this ICAI air-lift bioreactor. Oops, already 9 o'clock. And this has been constructed for the production of single-cell protein. So if you look at this, it's a very huge bioreactor, 1,500 meter cube, higher than 100 meters. So it's in this compartment inside. It's an air-lift bioreactor, of course, we already said it. And this was constructed in the 70s, where people have thought that it's a wise idea to produce food based on mineral oil, because mineral oil was so cheap. So in this bioreactor, what was done is they used methanol to grow single-cell proteins, and this was what was then used as feed. Then came the oil crisis, then it was dropped. But today, this reactor is still in use. They produce corn inside. So I don't know whether you know that corn is a product from fungi, which is used as a meat substitute, you could say. And they have a large array of vegetarian and vegan products. I also tried it. So during the week, as you might know, I don't eat meat. Corn, you find it also in the Edeka market next to the university. So check the vegan region stuff there. So, but my question to you is, I like this picture very much, because you have these cows before the conventional meat production versus the new meat production, which is no more relying on cows. And you know why is the meat production with cows problematic? Because their climate, these are cows and these are nice animals, but of course the main problem is, for the climate, a cow is the worst thing you can do. They have a really horrible carbon dioxide imprint. Carbon dioxide, one thing, and it leaves an enormous amount of water. So carbon dioxide equivalents, to be honest, because it's not just carbon dioxide, it's in the cow, you need to know it's methane. And the main problem is the fertilization of the soil, and you produce then N2O, and this is even way more climate active than carbon dioxide or methane. So the climate imprint of cows is horrible, and this is unfortunately also true for milk products and so on. So based on the climate, it might be wise to substitute. Whether that's all the best, if you use then fungi in these bioreactors, this is a matter of debate. You can also directly eat the soy instead of giving it to the cows, but that's another story. Okay, but my question, which goes to you, is please put the response in the chat. We have here a cooling tower. So this is in the UK. So it could be, of course, that we have nuclear power plant standing next to it. So my question to you is, why do we have this cooling power there? Is it required for the process, or is it just because of the picture, because there was some space left, and that you get these cows? This I asked you. Please put the answer in the chat. Now, if you compare stirred tank versus air-driven reactors, we can say the following. So as for low viscosity fluids, an adequate mixing and mass transfer is possible in this, let's say, reasonable reactor sizes, both for stirred tank reactors, bubble column, and airlift reactors. If you go up to higher volume, so 50 meter cube is already something. These are 50,000 liters. These are huge bioreactors. But if you go now from huge bioreactors to very large bioreactors, then air-driven reactors become more and more attractive, because the power input you need for stirred tank reactors in these dimensions is extremely high. So then these airlift or air-driven reactors are way better with respect to the economics. Yeah? And in very large reactors, you cannot bring in the stirrer power anymore. So in this case, it's not feasible at all to design such a huge reactor as a steel tank reactor. There, the only way is bubble column or in general airlift bioreactors. And this is only true for low viscosity fluids. If you go to higher viscosity, then a steel tank reactor is the only option. Because if you have a high viscosity fluid, you sparge in your air, the air just gets stuck there and there is no mixing, nothing. So you can only operate with high viscosity fluids. Mixing is brought in with your stirrer, and that's it. Of course, the higher the viscosity, the higher the stirrer power you need. And therefore, of course, a high viscosity bioreactor is limited with respect to the size. You cannot design a 1000 meter cube bioreactor for a high viscosity fluid because it's already, you need an enormous amount for a steel tank reactor. And in these dimensions, even with a low viscosity fluid, the power amount would be tremendous and feasible. And this is even worse with high viscosity fluid bioreactor. So you will not see such type of reactor in these dimensions. And the other thing is highly exothermic reaction. And now we have a look back to the question. Yeah, the cooling tower lowers towers there to prevent overheating. It's for cooling the bioreactor, because initially, remember, they were constructed for growing on methanol, and methanol, you remember, is highly reduced. So the heat of reaction is enormous. You remember we could calculate via an aerobic reaction by calculating the oxygen consumed, and at the end it's the transfer of electrons from our substance to my biomass and oxygen. And the higher the degree of reduction, the higher the heat I produce at the end. And if in these large scales, if you have high density, you produce an enormous amount of heat, and you cannot bring that away just by normal cooling. You even need these heating towers. That's the point. And if we now look back to this point, and this is exactly what is depicted here in this part. So if I have a highly exothermic reaction, like if I grow my biomass on highly reduced substances, for example, then the energy which is produced is very high, and the cooling demands are high. Now, if I go for a steel tank reactor, I need to bring out always need to bring out the heat of reaction. This is what I always need to do. But in addition, I also need to bring out the heat which I brought in with my stirrer. So the stirrer power, which is brought in the bioreactor at the end, is, of course, I move it, but at the end, the kinetics energy is transformed in heat. And this heat I also need to remove. So then the cooling requirements explode in this case. So this means for high exothermic reaction, steel tank reactors are not optimal. Okay. Now, bed reactor. This is an example. It's a packed bed reactor. Packed bed means it's not liquid, so we put them together, and it's like on your column for HPLC and so on. So this is often done with immobilized cells or enzyme, and then I just pump through my medium. If I do aeration, I cannot do it here. I can do that in a parallel vessel. Of course, the particles should be incompressible to do that. This is often done if I do bioconversion reactions and so on, or sometimes for production of aspartate and so on. So if I have a process where I produce gas, where carbon dioxide, for example, is being produced, this is not optimal, because this gas will be trapped in the packing, and this then disturbs the complete process. So this is only possible in optimal processes which are anaerobic, which I do not need to sparge. So if I have a bioconversion, I have dead cells anyhow in this case. Or if I have cells which I grow, which is anaerobic, then it's okay. So this is let's say, the drawback of this reactors. A fluidized bed reactor, there it's easier with gas trapping and so on. I have no problem. So I have again immobilized my cells or enzymes on these particles, and I operate it in an upflow mode until this becomes fluidized. Of course, in thermodynamics or in biophysics also, you might have calculated when this starts being fluidized and so on. As there is a constant motion, clocking and so on cannot happen, so that's an advantage. However, of course, you need a larger volume in contrast to the packed bed bioreactors. So this is for example, used for waste treatment with sand or similar material, for supporting the adherence of the microbes. And this is also used in vinegar production. And finally, we have the trickle bed reactor. So here we have liquid and gas phase. So there is the gas until down there, and you just trickle your liquid with which should circulate. Just you trickle it over the particles, which flows then down, and you pump that in this direction. So you have no continuous liquid phase. You can bring in easily the air here, and this is quite cheap to realize these types of reactors. So this is often used in aerobic wastewater treatment. If you have small scale wastewater treatment plants, then this is quite easy and cheap to realize. That's it for today. That was the last regular lecture, so I will then bring a video with respect to the chemostat operations, also with other reactor designs. We have some more slides, not too much. So this, you have the slides, so even without a video that would be possible, but maybe I make a short video. But nevertheless, thank you very much for your attention. Enjoy the weekend, enjoy the remaining day. At least here in Germany, we have now nice weather, so don't forget to swim as long as it's possible due to Corona. Stay healthy. Looking forward to seeing all of you again next week. Goodbye. And don't forget the evaluation. So the evaluation will be on until next Saturday, I think, or so. But it's of course cool if you do the evaluation before the lecture. I might already be able to check some suggestions of you, and we might be able to discuss that next time. That would be of course cool. And of course the evaluation only makes sense if more than 2 people participate, that it's a kind of a representative thing and not one who is says everything is super or the other everything is bullshit. This is not really helping. So I really read your suggestions. So for me, it's also important if you say this is not so good. It would be of course cool to know what is your suggestion, how you could make things better. Okay, thank you very much again, and goodbye, and looking forward to seeing you next week.